All right, today is day 2 of section 5.3. 5.3 is solving trig equations. We've solved trig equations prior to section 5.3, but they were relatively basic. They didn't require much algebra. They didn't require a whole lot of knowledge of trig identities. Okay, both of those things are going to be significantly more in play, meaning higher knowledge of algebra skills, higher knowledge of our trig identities. Yesterday, we did a run-through of some basic strategies to consider. Today, we're only going to be considering one strategy. All right, so reading our examples here, the instructions. It says, solving trigonometric equations by squaring both sides. Solve each equation in 0 to 2 pi interval. And they're telling us to be sure to check for extraneous solutions. All right, well, in quizzes and tests, you're not going to be told solve by squaring both sides. It'll be assumed that you can identify that that's a strategy that has to be done. Also, in quizzes and tests, one of the things you're being tested on is what do you need to check and what don't you need to check. The fact of the matter is you should be aware by the time you reach an assessment of this material which types of solutions need to be checked and which ones don't. All right, so assuming that we don't have those instructions about squaring both sides, how do we realize that that's the best strategy for this particular equation? All right, running through the things that we talked about yesterday. This equation has sines and cosines mixed together. Two ways we dealt with that yesterday. One of them was to factor this equation in such a way that it didn't matter if they were different. It's not possible. It's not going to work here. The second thing we did was we used some type of identity. Specifically, we were using Pythagorean identities in order to make a substitution in order to get it to be pure. Well, if we were to do that as is in the beginning of the equation, that would require taking sine squared plus cosine squared equal to 1. Solving for one of the two variable equations, rather, trig functions, it doesn't matter which one, it would take you to the same place. And it would mean introducing radicals into the equation. You would prefer, if at all possible, not to be doing a substitution that involves radicals. We're going to do some stuff later in the chapter where we have no choice but to do this, but for now we want to avoid it. If you did decide to do that substitution in the beginning, you'd have a variable under the square root, so ultimately you'd have to square both sides anyway. So all that being said, those are the clues that lead us to the fact of we want to solve this equation by squaring both sides. We can't separate it by factoring. A substitution as is way too messy. We're going to square both sides. So squaring the left means you're going to have to multiply out the binomial sine x plus 1 times sine x plus 1. You can't just square both. That's not valid when that's a plus or minus. The right side is pretty clean. Okay, now that we're here, we have sines and cosines mixed together, but because we have something to the second power, now we can do a nice clean substitution with the Pythagorean identities. Now, two of them are sines, and only one of them is the cosine. So it's much nicer to replace that cosine squared with 1 minus sine squared. Okay, now we're at the stage of the problem where we have a pure equation. Everything is just sines, but they're to different powers. When you have the same trig function at different powers, that's your indicator that you probably want to try to solve this by factoring. If you're going to solve by factoring, you need everything to one side, 0 to the other. That gets us to here. One thing we can do to make that a little bit cleaner, divide everything through by 2. That gets us to here. Now we can factor by taking out a GCF. Set that equal to 0. Set that equal to 0. So we have two possible solutions, rather. I'm sorry, 3. I don't know what I just said. 0, pi, and 3 pi over 2. All right. One of the things we talked about yesterday was some of these equations have a high risk of extraneous solutions and some do not. In an ideal world, you would like to be able to check all possible solutions to all possible equations. We don't have unlimited time for classwork, homework, quizzes, and tests. So we want to be picky in terms of, well, which ones do we need to check, which ones do we not need to check. When you are using the strategy of squaring both sides, that is high risk of extraneous solutions. These guys have to be checked. Now, yesterday didn't really go over detail of, well, how do you check it? Well, when you check for extraneous solutions, you want to make sure that you're checking back in the original. Sometimes you don't have to go all the way back to the original. Sometimes you can get away with checking an intermediate step, but to guarantee it being a valid check, you want to check it in the original solution. So sine of x plus 1 equals cosine of x. First possible answer to consider is 0. 0. So going to the unit circle, we know that the sine of 0 is 0. We know the cosine of 0 is 1. 0 plus 1 is 1. 1 equals 1. That checks. 0 is a solution. Okay, second, make sure I can see this. Second possible solution, x is equal to pi. So sine of pi plus 1 equals cosine of pi. Going to the unit circle, sine of pi is 0. Cosine of pi is negative 1. 1 does not equal negative 1. Pi is extraneous. So that one worked, that one did not. Third possibility to check, 3 pi over 2. So the sine, 3 pi over 2, plus 1 equal to the cosine of 3 pi over 2. So on to the unit circle. Down here, 3 pi over 2. Sine is negative 1. Cosine is 0. 0 equals 0. That checks. So we have 0, 3 pi over 2 as our final answers that check. The pi is extraneous. All right, next example. Secant plus tangent is equal to root 3. Two different trig functions in the same equation. Possibilities to consider. One, we can factor them away from each other so that it does not matter that they're different. Two, do a substitution. If they're both to the first power and we don't have at least one of them to the second power, it involves a substitution that involves square roots. You don't want to go there. If you substitute with the square root, then you have to square anyway. So if we're going to square anyway, it's a lot cleaner to square in the beginning of the problem. Okay, so we were told to square both sides from the beginning, but if they didn't give us that, that's how we would make that decision if that's the best way to solve this. All right, now that we're squaring, it's best to square when you have a trig function on each side of the equation. It tends to get exceptionally messy if you were to square both sides as is like that. That's going to lead to a nasty trinomial on the left that we don't want to have to deal with. So one of these two guys has to come over. It doesn't matter which one you bring over. It's going to take you to the same set of solutions in the end. Just pick one and bring it over. And then you have to square both sides. That's nice and clean. That binomial needs to be FOILed out. Now that we're here, we have secants and tangents mixed together, but at least one of them is squared. So if at least one of them is squared, we can make a nice, clean Pythagorean identity substitution. Since two of them are tangent, and that's the secant, it's probably better to make that substitution right there. That gets us to be a pure tangent equation. Well, one break that we get is that cancels with that, so that's nice and clean. So now we're back to a very basic strategy. Isolate that tangent. That gets you to here after you run through the algebra steps, and we get two possible solutions to consider. Pi over 6, 7 pi over 6. When you are doing equations that involve squaring both sides, high risk of extraneous solutions, you need to check to see what works and what doesn't. I already went through in the previous example how to do the check. I'm not going to do that again in the interest of time. Plug the pi over 6 into the original. Does it work? Yes or no? Plug 7 pi over 6 into the original. Does it work, yes or no? Identify what's extraneous and what's not. It turns out that pi over 6 is a keeper, the 7 pi over 6 is extraneous. All right. Third and final example for today. We have cotangent and cosecant mixed in the same equation. Running through options to consider when you identify that. Can they be factored away from each other? In this problem, no they can't. Number 2, could we do a clean substitution as is? Well, without one of those guys being squared, it's probably not. When you need to do a substitution in order to get the equation to be pure and everything's to the first power, that's your clue. You probably have to square both sides. Okay, if you're going to square both sides, you want one trig function on the left, one trig function on the right. So what this problem did is brought this over here. Now that we're here, you square both sides. That gets us to this equation right here. The Pythagorean identity is 1 plus cotangent squared is equal to cosecant squared. So we could replace the cosecant squared with 1 plus cotangent squared, or we could replace the cotangent squared with cosecant squared minus 1. It's going to lead to the same final answers in the end. It doesn't matter which one you choose for that. We did one of those problems yesterday where either substitution took you to the same place. Okay, now that we're here, we have a pure trig function cotangent, but it's to a higher power. So we want to isolate that. I did my flippage thing here. Square root both sides. Gives you your possible solutions. Remember, if you're going to do the flippage, the only safe place to do the flippage from here to here is when it's a single trig function on the left, single number on the right. If you try to do it up in a higher part of the problem, most likely it's not going to work. Every once in a while you get lucky. Even a blind squirrel finds a nut once in a while. But you don't want to do that flippage move until, right here, until you reach that trig on the left, number on the right, one trig term, one number term. Okay, so this gives us our list of potential solutions to consider. Each one of these needs to be plugged into the original equation, identify what works and what doesn't. In this case here, pi over 3, 5 pi over 3 turn out to be extraneous. The 2 pi over 3, 4 pi over 3 are valid solutions, part of your final answer. Okay, some overall notes here. Clearly, after watching these 3 examples, you realize these problems have a lot going on. They are significantly algebraically intensive. Okay, in the big scope of mathematics, this is the type of trig that you need to know for calculus purposes. The SOHCAHTOA trig that we started with in the beginning of the class is valid. It's important knowledge, but that's not what you need to know in terms of success in the trig world. This is, in the calculus world. This is the type of trig where it's not just sine is opposite over hypotenuse. This is like meat and potatoes, the trig you're going to be applying in calculus next year. So that's one thing of note of this is, I think, pretty much the first thing we've done that's had this level of both trig and algebraic intensity. Okay, second thing, a little bit more specific to what we're talking about now. If you were to see these types of equations, and it's a multiple choice format, in a multiple choice format, you're probably better off just guessing and checking from the very beginning. If you were to do this as is, to get all the way to, which would be a more extreme example. Like this guy right here, you have to do all this work to get the 4 potential solutions, to plug in 4 numbers to get your answer. Typically, in most multiple choice problems, there's only 5 that you have to plug in anyway. So if you're plugging in 4 numbers anyway, you might as well plug in a 5th to see what works and what doesn't. So as a free response problem, there are no cool math teacher secrets in terms of making this any quicker. This problem is what it is. Unless you're going to use some type of computer program or technology to solve it. Paper, pencil skills, there are no shortcuts to this particular problem as a free response. But, for example, if you were to see a question like this on a quiz or a test, and you recognize that I'm going to have to do all that work, I'm going to have to plug numbers in anyway, I might as well just plug them in from the very beginning and go that route in order to identify the answers. I think that pretty much wraps it up for what we are covering for day 2 of section 5.3.